Are we back?
Yes, we are.
You see, I just got a new Scholar email saying that one
we
of
are
my
live now, Matteo.
Oh.
So I think it is 11 o'clock UTC. Hello, Software Underground, and welcome to yet another 2 hours tutorial here at Transform 2021 with a quite unconventional start. Good to have you all here. I would like to start with thanking our sponsors, Studio X, also AWS and Agile. It's good to have sponsors which make it possible to have such events. If you follow live, please subscribe to the channel on Slack, Swang Slack, where we will help you to answer questions if you have installing it or running the notebooks. With that, let me introduce you to the speaker of today, Matteo Ravasi. It's a real pleasure to have him here. Matteo is an assistant professor at KAIST University, where he combines advanced numerical methods and cutting-edge computing technologies for imaging of the subsurface and more. Before starting at KAIST, which I think was in January, he used to work for Equinor, and this was also where he really got involved in open source, I would say. He started PyLops, what he's going to talk about today. And before being at Equinor, Matteo earned a PhD at Edinburgh University. That's actually where we got to know each other. And I think Matteo published in the first 6 months as many publications as I in my whole scientific career. So it's a real pleasure to have Matteo here, and take it off from here, Matteo.
Editor, thanks a lot. No, I don't think I published more than one paper in my first 6 months. But yes, so it was an unusual start, and I was trying to tell you, but apparently got broadcasted to the world, that PyLops just got a new citation from work in millimeter wave imaging, which I'm not really sure what it is, but hopefully it's a good start to the tutorial of today. And although I'm a geophysicist and I do work mostly with seismic data, I hope to give you a flavor of what this Python library called PyLops is all about, and where it can be used beyond the problems that I work on and the problems that you will see today. So if everything is working correctly, you should see the GitHub repository of the PyLops Transform 2021 repository, where you will be able to access the notebooks that we are gonna run today. You will have 3 options, well, 4 options actually. One, you can just listen to me for the next 2 hours and then try to play with the notebooks afterwards. That's good. You could also try to follow along and use a local Python installation if you want to do so. The easiest way is to either use the environment file or the requirement file here with either conda or pip installed. And if you want to know a bit more details on how to install PyLops with all the additional features that we have and we'll discuss today, follow this link. You can also use Binder. That seems to work fine. You will just click here, get Jupyter Notebook after a few minutes, and then you'll be able to use all of the 3 we're going to go through today. Or if you prefer Colab, that's also good by me. Here you have 3 links to the 3 separate notebooks. So I'm going to go off by using my personal laptop. And if you have a fairly small laptop, that should be good enough to run pretty much everything today. So let me start from the introduction. First of all, we want to discuss briefly, without going too much into the details, but just to get everyone on board. And even though that those of you that don't think they know inverse problems very well, hopefully in half an hour you will know, at least you will know some of the basics to get you going with PyLops and with your journey in inverse problems, hopefully for the future. We will also go through the main feature of PyLops and of similar sister libraries that you can find in other programming languages, if you prefer other, which is the idea of using so-called matrix-free linear algebra or matrix-free inverse problems. And you will soon understand why this is important, especially when you want to try to scale to large data sets, whether they are seismic data or data in other disciplines. So to start with in this introductory notebook, we will also look a bit into the main commands and operations that you can do with PyLops to create operators, combine them, solve simple inverse problems. And after that, hopefully you'll be able to get into more real-life problems like those we will have in the second and third notebook. So if you're not familiar yet with PyLops, you want to get started after today, these are your three main resources, I would say. The notebook, the repository for today tutorial, as well as the main GitHub repository where all the code and all the activities happen. That's where you can interact with pull requests or GitHub issues if you want to get in touch with us. And the reference documentation that we are quite proud of is very well kept, at least up until now. Here is what you will see is hosted on Read the Docs. And the main interesting part among the others are the tutorial section, where you will see a number of interesting tutorials of more or less real-life problems. And your main friend will be the PyLops API page, where you can go through and find out all the operators and solvers that are implemented and go through inside each of them. You should be able to see some description as well as at the bottom examples to get you going. So with this, we're going to just start with a bit of theory. Hopefully this is not too scary for those of you that are not remembering linear algebra very well from your university days. Linear algebra is a pretty simple concept, which we can look at it with this cartoon here. We have a vector x that contains a number of elements. We have a matrix that we call A, and we have a second vector y that contains another certain number of elements. What we generally want to do is, first of all, we want to be able numerically with a computer to apply the effect of this matrix A to a vector X to give us the vector Y. This is what we call the forward problem. And ideally, we would also like to do the opposite. So what we call the inverse problem, given Y and the knowledge of the operator or the matrix A, we would like to estimate X. If you're a bit more into math, you would generally say that A is a matrix on an operator that goes from a model space of dimensionality M to a data space of dimensionality N. And every time you apply A to X, what you're doing is what is called the forward model or the forward operation. Turns out that another operation that is very important to be able to do when we want to solve inverse problem is the so-called adjoint modeling or adjoint operation, which if you have an explicit matrix, let's start from a very simple case, this is equivalent to transposing the matrix. So if I go up, sorry, I'll just keep both of them. You see you are transposing this matrix and you are complex conjugating all of the elements in case the matrix has complex numbers. You can now apply this matrix to a vector of the dimensionality of the vector y, and you get the vector of dimensionality of the vector x. However, this is only a vector of the same dimensionality of x. This is not the same x that you had fed to the forward problem. To be able to get a proper estimate of x, what we instead need to do, we need to do or solve the so-called inverse problem, which if you're familiar with inverse problem or remember some courses that you did at university, you generally write on a piece of paper like this: x at, because will only be an estimate, is equal to the inverse matrix A times y. In practice, however, A may be a very, very large matrix, and inverting it directly is not always required and not always possible. Instead, especially for the sake of PyLops and today's tutorial, we will always rely on so-called iterative solvers. So these are solvers that, luckily for us, only require us to be able to apply the forward and the adjoint operation. And by a chain of forward and adjoint operation, and as well as other vector matrix operations, they can provide us an estimate of the vector x given the vector y. So this seems to be fairly simple and probably exactly the same as what you would have learned during an inverse problems course at university. So what is the difference when we talk about matrix-free linear algebra? If you want to look at it in a very, very simple, plain way, imagine that you don't need to have a matrix A explicitly defined, but all you need to know, or all you need to be able to do, is to write a piece of code, in this case, a piece of Python code, that fed a vector of dimensionality x will give us a vector of dimensionality y, which is equivalent as if we add the explicit matrix and we would apply it to the vector. Similarly, you will need to write a second piece of code that, given a vector y, will apply the same operation as if you had access to the matrix A, H, or A transpose. So you may wonder, why do you want to do that? You want to make yourself, your life harder. Why can't we just have the matrix A? We will see in a minute why this becomes important. But to do that, we need to tackle this question with a couple of numerical examples. So that will make it easier to understand. So we're going to start with what we call an element-wise multiplication, also called Hadamard product. And we're going to show that this operation can be performed using actually a matrix vector notation, and later how we can do that using a matrix-free formulation. We will also do the same with the first derivative, numerically first derivative. Now, if you want to run this in Colab, just make sure you uncomment this line and install the libraries that are not available in Colab at the moment. Since I'm running it on my computer, I'm just going to import a number of libraries that we will need for this tutorial. So let's look at element-wise multiplication. The easiest way to write this is to say that the element I of the vector y is equal the multiplication of the element I of a vector d times the element I of the vector x. So this is element-wise multiplication, as probably you all know. How can we recast this as a matrix vector formulation? And the reason we want to do that is because later on, for example, we will chain and combine multiple operators, and we want to always be able to know what is the effect of the operator as if that operator was a matrix. So if you are good with linear algebra, you will immediately realize that if you have a diagonal matrix times a vector, what you get as output is a similar vector, which, sorry, this is difference luck, a similar vector, which each element is now multiplied by each element of the corresponding row of the matrix. So you may see that these two operations are exactly the same. So now why I wanted to write this into a matrix form, this is because now we need to be able to write the adjoint. And my recommendation is always to write a small forward on a piece of paper and then explicitly write its adjoint. So we transpose the matrix and complex conjugate. And we see that, at least in this case, specific case, the adjoint is the same or very similar operation, is an element-wise multiplication now between the vector y and all the elements of the diagonal vector d, complex conjugated. If the numbers are all real valued, you will see that this is what we call a self-adjoint operator, because the forward and the adjoint are the same. So let's start using pure NumPy and pure dense matrix operations to see that this is possible, this can be done. And this is probably how, if you have are not familiar with matrix-free optimization, this is how you will tackle the problem. So we say we have a vector with 10 elements. We're gonna put them from 0 to 9 into a variable called diag. And then we use the NP NumPy diag routine that we can feed with a vector, and will give us a equivalent diagonal matrix with this vector along the main diagonal. So this is what you see, is similar to the cartoon we had at the top. Now, if we have an explicit matrix, we can easily apply the forward and the adjoint, and this could also serve for us as a benchmark to see if our matrix-free code is correct. So we're gonna now create a vector of ones, and we can simply use NP dot between the matrix and this vector, or any other flavor of np dot, as you prefer. And we see that we get a vector from 0 to 9, not surprisingly. Now a bit more complicated is what we can do if we want to get the adjoint. Since we have an explicit matrix, we can simply transpose it, apply the complex conjugation, and now apply the np dot to the transpose and complex conjugating matrix times the vector y. And this is the result we get. So you see now a dimensionality of the vector x, but very different from a vector x where we had all elements equal 1. So this is because we are doing just an adjoint operation, not an inverse. So far so good. Why do we bother trying to go one step further and use what we call linear operators, so matrix theory, linear algebra? Where I see, and hopefully you also see, two main limitations of the approach that we have just discussed. We are storing n square numbers, even though we could only store n numbers, those along the diagonal, and just know that the operation we want to perform is equivalent to element-wise multiplication without having to store all the zeros of diagonal elements. Also, when we apply a dot product between this matrix and a vector, we are doing n square multiplication and summations, but ideally we could only do n if we just apply the element-wise product between these two vectors. So this is exactly what linear operators do. And we're gonna take a look at this cell where we are writing a very minimal definition of a PyLops linear operator. So you immediately have a quick look and a quick glance at how the operators are implemented inside PyLops. And it's fair to say that we start actually from SciPy linear operator class, which we then overload and enrich with more features, both methods and properties. But eventually we are using the exact same syntax. So we need to implement a function, a method called underscore matvec, which applies the forward operation, and a underscore rmatvec, which applies the adjoint operation. Later on, we can access them using more expressive notation, and you will see that in a minute. And if you're familiar with object-oriented programming and objects in Python, we also have this init class on which we are storing some useful information to begin with. In this case, for example, this diag vector. So it's not surprising that the main operation that we are performing here is just an element-wise multiplication. Remember, if you have two numpy arrays, the star will apply element-wise multiplication. And for the rmatvec, we simply complex conjugate this vector diag, and again, element-wise multiplication. So now we have not created an explicit matrix, but if we instantiate what we call a diagonal operator, we call it diagonal because the matrix looks like a diagonal matrix, the matrix equivalent to the element-wise product. Now we can see that we have created a PyLops operator, and if we print it, we get some information. We can now apply the forward and the adjoint, and we can either use the star or the at, similar to what we could use for NumPy. And we see that what we get is the exact same result that we got when we had dense matrices. Same for the adjoint. Now we can simply use the following syntax. We take the operator .h, and then we apply the star. And again, we get the exact same result. So as expected, or at least for me, we are getting the exact same results, even though our implementations are substantially different. So let's try to make the vector x a bit bigger and do some timing of operations, both if you add a dense matrix D, as well as if we put this diag vector into a SciPy sparse diags matrix, as well as if we use PyLops linear operator. So we're going to run this, and we will see that the cost of np dot with a dense matrix is not surprisingly very high. In this case, SciPy is very efficient because it's pretty much doing under what we are doing in this case with PyLops. But still, for this specific run, PyLops was slightly faster. So the advantage of PyLops is that you will see, as you will see soon, when we start chaining operators, if you had to create sparse matrices for each of them, and then you directly multiply them up front, your equivalent matrix will almost always become less sparse, and your final computation will start to be less and less efficient. While with PyLops, we can chain any linear operator we want, and the eventual overall cost will be the sum of the cost of applying each operator in the chain. There is, of course, a complication arising when we want to implement linear operators versus having dense or sparse matrices. As I already said, we need to know how to formulate and implement the adjoint. And it's not always that easy. It's not always like in the diagonal case that we immediately realize that it's pretty much the same operation apart from the complex conjugation. So how do we ensure that when we implement forward and adjoint, we can validate them, we can ensure that they are correct and use them to solve inverse problems? Luckily, there is something called the dot test, which is a very powerful test based on a very simple observation that we can make using very basic linear algebra operations. So let's start here on the left. Let's imagine we have an operator A and two vectors, U and V, filled with random numbers. One of the dimensionality of the model space, U, and one of the dimensionality of the data space, V. We can now apply the forward, so H times U. This will give us a vector in the dimensionality of the data space. And then we apply the dot product between these two vectors. This will give us a scalar. Now let's do some simple manipulation. If you remember, if you have a matrix times a vector transpose or adjoint, you can write this as the vector adjoint times the matrix adjoint. You see here, vector adjoint times the matrix adjoint. And finally, we can use the distributed property of the dot product, and we can say that we now want to apply this operation first, which will give us a vector in the model space, times this vector in the model space. And we will get again a scalar. Since what we have done is correct from a mathematical point of view, if we now apply our numerical forward and our numerical adjoint, we should expect this equality to be satisfied. If that is the case, we have a good indication that our adjoint and forward are correct. This is not a necessary. This is not a sufficient condition. It's only necessary. So if you are into math, you will say this is not 100% sure that we are doing them correctly, but experience tells us that most of the cases passing this test is a good sign. So you can use the PyLops dot test that you can find into PyLops utils dot test. You pass the operator, you can pass the input and the output sizes. And if you say verb equal true, you will get some verbose output, which tells us, not surprising in our case, the dot test was passed. And these are the two scalars that we get. You see pretty much exactly the same, in this case, to 6 decimals. Let's move on to something a bit more complicated. We want to implement the first derivative. So let's imagine you have a straight line. You're going to pass it into a operator that applies the first derivative, and you will get out a constant. We're going to use a first order center first derivative stencil. You could use forward, backward, or even higher order if you prefer. And this is how the forward looks like for a 3x3 matrix, or a vector, input vector of 3 elements. We can always apply the adjoint, and we can look how this looks like and try to get some insight how we should implement the forward and the adjoint. There are 2 ways to implement this. The first one is to realize that if the forward is performing what we call a sum operation, so we are taking, if we look at this middle line, these 2 elements, x0, x2, and doing a weighted sum, the adjoint is generally doing what we call a spread operation. So we take now the second element and we are spreading it half here and half here with a different sign. So that's one way to see how you could implement it. The adjoint of a stack operation is a spread operation. I actually prefer to look at this problem more from a signal processing point of view. We can see for the first derivative as the convolution between your input signal and a very compact filter of -0.5, 0, 0.5. So now if you want to do the adjoint, you can just think about this as, let me do the convolution in the frequency domain. So the adjoint will be doing the convolution with a complex conjugate, which means we'll be doing the cross correlation instead of the convolution. And this gives us the insight. And actually, this is how the first derivative is implemented when it comes to using our GPU backend. We'll come back later to this point. We prefer to offload this operation to efficient convolution and correlation operations, whether they're in SciPy or in CuPy, because we have realized that this is how you could implement a first or a second or any order derivative. So here we're going to start again doing the dense matrix formulation. This looks like in the cartoon, with the only difference that the first and the last line, we are doing it using a forward and backward first order derivatives. Otherwise, we will end up outside of the available data space and model space. We're going to also, in this case, use PyLops first derivative. If you are interested in the implementation, please just go inside the code and take a look. And we're also going to use this edge equal true, which basically implements the exact same operation at the edges that we have done here for the dense matrix. First of all, we validate that this passes the dot test, and we see it does. And this is what we have for every operator of PyLops. If you look at our unit test suite, every operator has a dot test, and no operator that doesn't pass the dot test makes it into the library. We also have now an example in which we want to see, once again, that these two operations are the same. So we're going to make a straight line from -5 to 5. We apply the forward and both with the dense matrix and with a PyLops operator. And not surprisingly, if this is y equal x, the derivative of y will be 1. Now we can apply the adjoint. Again, in both cases, we get the same result. And once again, you see that we are not getting back our straight line, because this is not the inverse. It's just the gradient or the first iteration of an iterative solver. So we're going to go in a minute and see how we can actually try to invert for this straight line, given a constant. But before, we have briefly looked into the computational cost of different type of strategies using dense, sparse matrices or PyLops operators. Here, we also want to look at something slightly different. We want to look at the memory footprint, because I mentioned before, we can also relieve some of the heavy memory footprint if we don't make dense matrices. We are using the Pimpler library to actually get the size of the NumPy array. And we're going to do that, again, using both our dense matrix notation, sparse matrix notation, and the PyLops operator. So we're going to run this, and you will see very quickly, if we look at the memory requirement by increasing the size of the operator, how we are plotting it into a logarithmic scale, how the memory requirement of the dense matrix is growing as an n square. The one of the sparse matrix is growing much smaller, because all we need to do is to store 2 diagonals. But the one of PyLops is actually constant, because since we have told our operator that we want to do a first derivative, all the operator needs to know and store is the step size. Everything else can be done on the fly when we apply forward and adjoint. So hopefully you understand even more now why it's important when it comes to real life larger problems to move from dense matrices, which are easy sometimes to implement, to linear operators that maybe are less easy, but that's the gain you can get. And you can run this with 1 million samples signal probably on my laptop, while for a dense matrix, you will start to get into memory issues and you'll need to push yourself to a bigger machine. So finally, since it's not nice to just solve a forward problem, what we are more interested in is solve inverse problems, we're going to compare a dense solver from SciPy, which we can feed with a dense matrix and a vector, data vector, together with the PyLops backslash, which is one of the features we added to our linear operator class. This is an overload of a iterative solver, more specifically of the SciPy LSQR solver. So we can always call the LSQR solver directly and tune it with more input optional parameters. This is just something very quick and very expressive if we want to do quick texting. But we see that in both cases, we get back our straight line. Here there are some rounding errors, but in both cases, we have been successful. So this is the first time, if you have not played with PyLops before, that you hopefully see how inverse problems can be solved both with dense matrices as well as matrix-free formulation. Let's move now to something slightly more interesting, because so far we have seen a fairly schematic procedure. You make an operator by defining your forward and the adjoint, and you can apply the forward, the adjoint, and you can also invert the operator. But if every time we had to create an operator, this library will be fairly useless, at least from a user perspective. What is nice instead is that if you create a suite of operators, like those that you have already seen are available in our library, you can now combine them in different ways. You could, for example, think about summing them, chaining them. You could stack them vertically, horizontally. And the overall operator that is created by combined multiple operators, again, could be easily applied to a vector. We could easily apply the adjoint as well as the inverse. And this is the power, because now you can look into most of our operators, try to combine them in a smart way to solve problems that perhaps we have not solved yet, and perhaps are problems that are of interest for you and for your research. So here we just, again, do something fairly simple with the main difference that instead of applying a derivative to a straight line, we apply it to an Heaviside function. This gives us a spike. And we say that we are not satisfied. We also want to apply a smoothing operator that smooths these spikes around. So now we have this boxcar, and we want to see if we can invert the chain of these two operators to get back the Heaviside function. Can we do that? But let's look at this code here. So we're going to start by defining our vector x, which will look exactly the same as in the cartoon. We then define the first derivative operator, as much as we did before. And we also define the so-called smoothing 1D operator, which we can provide with the number of samples we want to smooth, so 5, as well as the number of sample of the output, in this case, the same as the input, nx. Now, chaining two operators is as easy as using the star in between the two. So you may notice here that something happens different from before. So when we apply the star, to an operator on the left and an umpire array on the right, this was invoking the forward of the operator itself. However, if you apply the star to two operators, PyLops will understand that and combine them in what we call a chain of operators. Now later you can apply the chain to a vector, and PyLops will unravel the chain for you directly. So it will first apply the op to x, we'll get the vector, and then apply sop to this vector and give you the output y. If you now apply the adjoint, this will apply this chain of operators in reverse order, and each operator will actually invoke its adjoint, not its forward. Same happens if we use the backslash within the iterative solver, in this case, LSQR. And finally, we will see more later. We have here shown a simple example of one of our what we call the wrapper of least square solvers, where we can solve regularized or preconditioned equations as well as the normal equations directly. And from a user perspective, this is boiling down to the following. We can provide an operator. We can provide a set of regularizers. In this case, we just provide an identity matrix. So we just want to do a standard Tikhonov regularization. We provide the data, and we can also provide all the different data of the regularization terms, as well as some weights. So let me briefly go here in the documentation to make this a bit more clear. If we go into the normal equations, you will see that what we are asking PyLops to solve is this equation where we have the modeling operator, a set of regularizers, and the same on the other side. So instead of doing this all yourself, you can just invoke the PyLops normal equation inversion for you, and this will be done under the hood. And the final normal equations will be fed to the same solver as before. So we run this, and we see that not surprisingly, we get a fairly good estimate of our heaviside function. Last example in this introductory tutorial, and from now on, I'm just gonna use geoscientific examples. I think most of the audience here is folks working with subsurface data. So hopefully you will find a couple of interesting applications that perhaps up to today you have been only solving using commercial softwares. And you can see how this can be very easily done using in a programmatic way, using Python and PyLops, and the advantages that this can entail. So here we are looking at the problem that if you have been a geophysicist in an energy company or other company that deals with geophysical data, you may have been working on this type of problem many, many times. This is a so-called problem of a well tie. Imagine you have a well with some well logs and the seismic data passing through, and you would like to tie the response of the seismic data to a model response, seismic response at the well. As part of this operation, you will always need to make an estimate of the wavelet that is in the seismic data. There are many ways of doing so. The most, I would say, rigorous way is to create a synthetic seismic data from the well logs with a wavelet or initial guess of your wavelet, and use the record this seismic data as the data of your inverse problem that you want to solve. So we're going to try to solve an inverse problem for the wavelet such that when we apply the wavelet and we use a modeling operator, in this case, we're going to use a pre-stack modeling operator, we can estimate what we observe in our seismic data. So this is an inverse problem. If we write it in a compact form, we have D equal GW. And if we know how to model G and we have access to a certain data D, we can make an estimate of W. Again, there are different ways of doing so. You could do this in the frequency domain. What we suggest here is to do it as a time domain inverse problem. And it turns out that this is the best way. You can allow your inverse problem to be well posed. You can add regularization terms and preconditioning, as you will see in the next 10 minutes. So just to start, this is pretty interesting, I would say, boilerplate code. We are just creating some synthetic VP, VS, and raw profiles. As well, we are creating a Ricker wavelet, which we will later assume we don't know, and we're going to try to estimate. So this is our VP, VS, and raw logs. Fairly unrealistic, though. This is how they look. At this point, we can combine VP, VS, and raw, actually the natural logarithm of VP, VS, and raw, into what we will use as our model vector. We can then take advantage of PyLops pre-stack wavelet modeling operator, which implements the equation you have seen above. So we say that this is the model or the subsurface properties that we want to provide to this operator. This is the set of angles if we want to model pre-stack data. And also we provided with some information about what is the expected size of the wavelet we want to estimate later on. And the modeling can be done with different linearization of the Zoepfel equation, and here we're using the Aki-Richard linearization. So now that we have the operator, let's assume that we want to create our seismic data. So we apply the operator to the wavelet and we get our seismic data. Now to make this a bit more interesting, we can add some noise. Assume you are really using some real seismic data. You never expect that the data that you observe is the exact exactly equal to the modeling operator times the wavelet, even if you are able to get a correct wavelet. So this is what we see. We have a pre-stack adder with a zero-phase wavelet. This is the noise that we are adding. And for a single trace, you see the black line is the noise-free and the red is the noisy data. So now what we want to do is we want to use this and try and also use the knowledge of the well logs so we can make the modeling and try to estimate the wavelet. We're going to start again using the backslash, just a very simple, naive inversion. This will not add any regularization or preconditioning for you. And we will see immediately, we can just look at these two lines for now and at the plot, that if we do that, we apply the inverse to the noise-free data, we will get a very nice looking estimated wavelet. But if we do this to the noisy data set, the estimate that we get is this very ringy and very noisy wavelet. And this is because solving inverse problems is never easy, especially when you have noise in the data or the operator is not well posed. And so in order to still be able to solve inverse problems and get value out of your data, one of the most popular strategies is what we call regularization. So regularization means, if you are more a statistics-oriented or a Bayesian-oriented person, means adding prior information to the problem on how you expect the solution to be. So in this specific case, we are expecting our wavelet to be smooth and well-behaved. And what we can do, we can add the regularization term that will penalize roughness in the solution. And this can be done by estimating the second derivative of your current estimate of the wavelet and adding a penalizing term to your cost function that says if the wavelet is not smooth, I'm going to try to get a new estimate that is smoother than the one before. This is eventually what happens under the hood into an iterative solver when you add the regularization term. We're going to do this using the PyLops regularized inversion. In this case, is similar pattern to the normal equations you have already seen. Provide the operator, we provide one or possibly more regularization terms, and we provide, in this case, the noisy data. And we also say what is the weight that we want to give to the regularization term versus the weight we're going to give to the data misfit term. I'm going to run this, and you will see that in less than a second, you get a much nicer result. If I, just to make you convinced, if I remove the estimate from the noise-free as well as the estimate from the noisy without regularization, you'll see that what we get is this purple line, all very, very close to the true response. And you can always play with this. I will leave it to you, but you can add more or less regularization and your solution will start to be even smoother. This is generally something that you have to decide as a user. Finally, even though in this case, I still believe regularization is a better solution, I show how you can also use preconditioning. Preconditioning is a slightly different way of adding prior information to your inverse problem. Instead of adding an extra term that says you want your solution to satisfy the data misfit as well as penalize some condition, for example, in the previous case, we want to penalize roughness in the solution. Here, when we precondition the problem, we feed our current solution through another operator, which will try to make it as closer as possible to the prior knowledge or the prior information that we have. In this case, we have two prior information that we would like to enforce. If we are trying to estimate a zero-phase wavelet, we will try to enforce symmetry in the solution, which if I run again this code above, you can see that here is definitely not satisfied. The green line is not symmetric with respect to the center of the wavelet. And also we could try to say that we want the solution to be smooth, so we pass the solution through a smoothing filter. We have, in this case, both the solution only with a symmetry operator, preconditioner, as well as the chain of the two that you can see here. And if we run it, we see that we still get nicer results than before, better than the previous green line, if you remember. The solutions now are both of them symmetric, but you can see that it's a bit harder in this case with preconditioners to remove the high frequencies that you have due to the noise than if you use regularization. So this is a way to basically say that there are multiple tools that you can use when you solve inverse problems, and by providing all of them, we hope that you will find the one more suitable to your problem. So we are 45 minutes into. I think I'm going to start the other notebook, and then at the hour, we will take a 5 minutes break. Dieter, tell me if this is okay. If I don't hear you,
that is fine.
Okay.
You can also, if you want, you can probably click on your video to have it a little inset if you want that the watchers can see you.
Oh, that's okay.
That's okay. Okay.
I'm not so beautiful. Okay, so let's go for example number 2. This is something maybe a bit closer to geophysicists and geologists that deal with the interpretation of seismic data or any other type of geophysical data. It is actually heavily inspired. I would say is almost a replication of a Jupyter notebook that Sergei Fomel created using Madagascar, and is to show how some of the tools that are available in Madagascar can also be accessed, in this case, with our own implementation, of course, using PyLops. It's not to say that one is better than the other, but it's to give you an idea of what are the functionalities of PyLops versus other geophysical open source libraries. We're also going to use a seismic horizon that Matt is very familiar with. To my knowledge, was used for the first time by Matt in his 2007 smooth operator paper, and is the same that Sergei uses, so I'm also using it. Now, the problem, as you see from the title, is to try to fill holes in horizons. So imagine you have a seismic horizon you have interpreted, and in some areas you may have been sloppy or you may not have been able to interpret it, and you want to give it to a geomodeler that is going to use it to create a subsurface model. Likely, the geomodeler will ask you to fill holes, and you will be left with a lot of manual work, and most of the time with a lot of guesswork. So what if we try to use an inverse problem to fill these holes? Of course, it will never be perfect, as much as you will never be perfect in doing so. And the way we're going to frame this problem is what generally in the computer science, in the computer vision community is referred to as in-painting. What does that mean? It means that we want to solve an inverse problem where we have a data term where we say that the solution at the locations where we have our interpreted horizon should be the one we have interpreted. And to fill the holes, we say that we can expect the horizon to be transformed to a domain where its representation in this domain will be sparse. This is a very popular approach. This is what generally is referred to as sparsity promoting inversion, and is used in many communities, including geoscience. And this problem boils down to optimizing this cost function, where we have this term where you minimize the L1 norm of the model in this sparse domain. We will see that since horizons are a bit closer to natural images than seismic data are, we could use the same strategy that is used in natural images, and the wavelet transform is a very good sparsifying transform. We will also play with another possibility, which is the 2D Fourier transform. Again, if you run this in Colab, make sure you run this cell. Otherwise, just go ahead like me and import the libraries we need. We're going to load the data. For simplicity, I just place the data in this folder in the notebook, in the repository. But if you want, you can also fetch it directly from Madagascar using this command. I'm following the exact same step as Sergei. The data is in an ASCII file, so I'm not entirely sure if this information is actually available anywhere, but apparently these are the X and Y coordinate of the horizon. And Sergei is also applying some tapering at the edges. I am not doing that. I don't see this as a need. And finally, we padded to the closest multiple of 2 so that the wavelet transform can easily be performed. This is, again, not a real requirement. Within PyLops, the wavelet transform, we do the padding on the fly for you, but let's do this to make it simpler. And this is what the horizon looks like. Those of you that don't like the jet color, I'm trying to do a one-to-one, and I have nothing against the jet color. If you don't like it, you can easily change it later on. So now we create the same holes that were created by Sergey. So 1, 2, 3. These are 3 nice locations because here the signal or the horizon is fairly well behaved. Here we have a bit more transition between red and green. And here we have a very sharp transition, is this channel looking like feature. So we're going to expect that, or at least if I were to look at this problem before trying to solve it, I would expect that inversion will struggle more here than in these 2 other holes. How do we do this? Well, first of all, we're going to create the wavelet transform. And to do that, we're going to use 2 different approaches. We can use a 1D wavelet transform that we have in PyLops available under the DWT operator. And we're going to do it first in one direction and then in the other direction. Or we could use actually directly the 2D wavelet transform that pretty much does this for you under the hood. This wavelet transform is actually implemented in PyLops as a wrapper to PyWavelets, and they provide a very large number of wavelet bases. Wavelet transform has been a toy for mathematicians for many years. It's very powerful. For example, is used for compression of images, for example, in JPEG 2000. So there is a lot of research that gone into making the best sparsifying transforms. And we're going to use one specific wavelet kind called the SIM9. So if we run this, once we create the operator, you should almost feel like at home. You are combining these 2 into a unique operator, and then we are applying the forward and the adjoint. And this is a very special type of operator because the adjoint is equivalent to the inverse. This is not always the case. It's a special case. For example, the wavelet and the Fourier transform, both of them are special cases where the adjoint and the inverse are the same. And you see what happens. If we take the image, this is what the wavelet coefficients look like. And you see why we can enforce or try to leverage sparsity, because this image can be represented by just a very few coefficients, those that you see here in white, and everywhere else is pretty much irrelevant. And if we just do the adjoint, we see the reconstruction is perfect. So now we want to solve an inverse problem, the one you have seen in the equation at the top. And it turns out that solving inverse problem with L1 norms is not as easy as solving least square problems. However, again, luckily, the mathematical community has been working quite a lot in the last 2 decades in implementing a variety of optimization routines for this type of cost functions. And here we're using a very powerful solver called FISTA, fast iterative shrinkage thresholding algorithm that is actually a specialized solver of the more general family of so-called proximal solvers. And remember proximal solvers or proximal algorithms because we'll come back to them at the very end of this tutorial. This is very similar as the other solvers we have seen before in PyLops. You feed it with an operator with some data, and of course you say how many iterations you want to run it for, and also the same weighting factor, how much you want to weight your regularization term versus your data misfit term. We're going to run it. There are different types of thresholdings that we can apply. Here we are applying a percentile threshold. And we see that in 3.5 seconds on my laptop, we get the result. We see how the cost function is decreasing, and this is what we get. So this is the original image. We didn't feed this image to the solver. We fed the image with the holes, and this is the result that we get. And here is the difference. We see that, as I already mentioned, we get some small error here. We are not really perfect in reconstructing this channel, but in the other 2 holes, we are almost perfectly reconstructing the signal. So instead of doing it manually and with a lot of guesswork, if you have some holes in your horizons, this is a nice strategy that you could adopt. And this is the horizon look a bit bigger. So we're gonna finish this. I still have 6 minutes, and we're gonna run the exact same workflow, but simply changing the sparsifying transform. So you're gonna use FFT 2D. You could use many other transforms. Some of them are kindly implemented in PyLops or in sister libraries, like the very popular curvelet transforms. Some of them are out there. They have nice Python implementation. They have not made it into PyLops yet. You could try, or you could ask us if you're really interested in a specific transform that you don't see. So we're gonna start again by creating the the Fourier 2D transform, applying the forward and the adjoint, and we see that what we get is, of course, a perfect reconstruction because the inverse and the adjoint are identical. And this is how the image looks like in the KK, KX, KY domain. So you see, again, very few coefficients, very close to the zero wave numbers, can represent this image. So again, we can think of using the Vista solver, feeding it with an image that contains some of the holes and see if we can get a good reconstruction. Again, this runs almost as fast, 3 seconds, and the results are very similar. I would say if you look in details at these two red and blue dots, I would say the reconstruction is actually slightly better with a 2D Fourier transform, but the main point of this tutorial is to show how you can take a problem that has actually fairly complex regularization term, an L1 regularization, and solve it very quickly and efficiently in PyLops. And with this, I think, Dieter, we can go for a break now and come back at the hour. Or if anyone has any question, we can take it and then take the break afterwards. Up to you.
Yeah, so far I don't see any questions. But to the hour, it's only 4 minutes, so you might 3 minutes. So you might add a bit more.
We come back at 05.
Yeah, that's fine.
So if someone has a very big house, they can go and grab a drink. Okay, 05, we are back. Are we back?
Yes, yes.
Yes. Can you see me now? I think I turned my camera on.
Yes, now it's good. I can see you now.
Yeah. Very good. All right. So I also checked myself on Slack. Apart from expected complaints from the color bar, I don't think there is questions, right?
No, not so far, no.
Not so far. I'll just do this before we move on to the next notebook. So.
Now your stream seems to be frozen.
Frozen?
Yeah.
You not see me changing color bar?
Now I see me.
Okay, let me just reshare.
Let me switch off mine. Yeah, now
What
I see
about
it.
now?
Yes.
You now see a new color bar?
Yes.
Very good. Okay, let's move to the very final example. Unless someone has any question. No? Is that correct, Dieter? No questions?
No, doesn't seem to be the case. No.
Okay, very good. So we're going to move to a very final example that perhaps some of you have already seen. I've actually done some of this work maybe a year or so ago when the Volve, or probably a year and a half ago, when the Volve dataset came out. The Volve dataset is a very nice dataset from my former employer. It's very nice in the sense that we have a lot of seismic data now open source, but they are just a bunch of seismic cubes. They have no well logs, they have no well peaks. So doing very interesting work is not that easy. But with Volve data, we have access to well logs with pre and post stack data. So it's a very nice data to play with if you're interested to showcase some of your techniques. And this is what we're going to do here. We're going to look at you will think is a fairly simple problem. It's probably the bread and butter of geophysicists that do quantitative interpretation. It's the problem of post-stack inversion. So we can look at this equation as the approximation of the AVO or Zurbrigg equation at zero angle of incidence, where we say that the recorded data can be expressed as the convolution between the wavelet and the first derivative of the natural logarithm of the M, which is in this case is the acoustic impedance, times 1/2. So what is useful from this formulation is that if we write it into a matrix vector notation or a linear operator notation, we can, given some seismic data and some knowledge about the wavelet, we can try to solve this problem and make an estimate of the acoustic impedance model of the subsurface anywhere where we have access to our seismic data. And of course, having access to acoustic impedance means that we can perhaps predict porosity or predict other properties of our rocks or lithophases. Now, this is a simpler problem than, for example, full waveform inversion or even pre-stack inversion. But being simpler is a bit faster and easier to run on a small machine. And we can, in this case, without losing any generality, because you could change your operator to be a pre-stack inversion, for example, we're going to look at different ways of regularize the inverse problem, trying to get the best out of your data and prior knowledge of how you would expect the subsurface to look like. So we're going to solve the problem with three different cost functions. You will see that the data term is exactly the same everywhere. Is L2 norm on the difference between the observed data and the model data. But we're going to, first of all, try to solve it in a fully least square sense, where we're going to add a second term, a regularization term, that tries to penalize the Laplacian, so the derivative over x and y. And in the 2D example, will only be over x. And this means that we try to get a solution that is smooth along the planes, the different time or depth slices. The reason we want to do that is because generally data contains noise. So if we do not add regularization, we can just try to invert the wavelet, we will get very ringy and noisy solution. However, we know that the subsurface is hardly smooth. We expect, especially in the depth direction, to have fairly sharp changes when we go from a formation to another, maybe from a soft sand to a hard shale. So what we can try is to leverage more advanced regularization terms. For example, we can try to also enforce a L1 norm on the derivative over the z direction. What this means in a mathematical term is that we want to try to enforce sparsity of the derivative of the solution, or in other words, we want to try to get a solution that is blocky along the z direction. Finally, we're going to use a very popular regularization technique used in geophysics, as well as very popular in medical application, what is called the total variation regularization, which tries to enforce piecewise continuous or blocky solutions along any direction. So not just Z, but also X and Y. The reason we do it in steps is because we need to go from a simpler, cheaper solver to a more advanced and more expensive solver. And we will see how the solution changes, and of course, users will decide whether it's worth the effort or not. And some people, from my experience, like to interpret things looking different from some other people. I don't think when I interpreted data myself that the way I like to look at things is not the way others or everyone else likes to look at things. So having more solutions allows more people to choose what they like best. So we're going to start. I think there has been a tutorial this morning where Jürgen presented some work with the Volve data and already discussed how you could access the Volve data from the Volve or the Equinor data village. Here are some more details. Basically, it boils down to realizing that the data is stored in Azure into an Azure blob container. So if you are familiar with Azure, you probably do this every day. If not, it all boils down to installing a Azure CLI library and run these ugly looking commands that tells you where to look at and which data to download. And if you want to do that yourself, feel free to do it, because you will have to retrieve the data. We cannot provide it here, it's too large. But you need to access, you need to provide a token here in this command and the following ones. And to provide a token, you need to register and authenticate to the Data Equinor website. Then you will be given a token. So follow the instructions. They should be bulletproof. If not, get in touch. In this case, we assume we have accessed the data because I downloaded it up front. And so we're going to do a workflow composed of 4 steps. You could think that the last 2 are the more interesting, the more challenging, but for the Volve data, it actually turns out that the first 2 are not as trivial either, even though they do not really require any PyLops intervention. So the first one is we just want to open the data and load it into an NumPy array, and it turns out that the Volve data was not stored into a regular 3D volume, so we need to do a bit of playing about with indexes. And also when we want to do post-stack inversion, we want to have an estimate, a prior estimate of a smooth background model, in this case an acoustic impedance model. And to do so, we will use a velocity model from the velocity migration model from Volve, and we rescale it to be a acoustic impedance equivalent. This part has been done separately. I'm not going through the details. What I basically did here was to cross-plot the well log and the seismic velocity model at the same location and perform a very simple linear regression to go from velocity to acoustic impedance. So here we're going to just assume we have a background model. And after that, we will look a bit more into the interesting part of how we apply inversion with PyLops. So we're going to run this cell. Once again, if you are in Colab or Binder, make sure you, or actually only in Colab, make sure you run this first and make sure also you download the data. Provided you have everything, we can go. And you will notice that there are two commented lines here. They are only needed if you want to try the very last cell of this notebook when we are using our newly created GPU backend powered by CuPy. But of course, you need to have a machine with a GPU, which is not what I have in my laptop. So I'm commenting this out for now. So let's start by defining a number of input parameters. For the sake of this tutorial, I'm just making the database smaller, but choosing a time region as well as subsampling by a factor of 2 inline and crossline. We choose some of the parameters for the wavelet estimation and also for inversion. Let's look at the data. So we're going to load the data using Segi.io. We're going to open it ignoring the geometry because, as I said, there is not regular geometry to make our life easy. And we're going to collect all the traces and as well as the inline and crossline and figure out how we can regularize this. This is interesting. Most of the time in real life, you'll end up having someone giving you a data that is not regular. So if you're interested and not familiar, I recommend you to spend some time here. But for the sake of this tutorial, we'll just assume that everything is perfect and the data now along a single inline looks like this. I'm not sure this is the best color bar. Again, feel free to choose the one you like the most. Now we're going to read the velocity model, which to make our life easier in this case is in a regular grid, but is in a different regular grid from the data. So we're going to use a SciPy regular interpolator to bring it to the exact same grid as the seismic data so that eventually we can plot our velocity model, the data in the area of interest, and the velocity model in the area of interest. As I said, we need to try to rescale the velocity model into an equivalent acoustic impedance model. These are the intercept and gradient coefficients that I got from my analysis with the well log. And so this model now looks more like in the range of the acoustic impedance. Wavelet, we could do different things here. Of course, we could use the well-tie code that I showed before. We will need to bring in well logs and do a bit of playing with this. For this tutorial, to make things easier, I'm using a pure statistical wavelet estimation where I just statistically estimate the wavelet by bringing my data to the frequency domain, making a frequency spectrum, and assuming that I have a zero-phase wavelet. And this is how the wavelet looks like in shape. Now we're going to do start from 2D inversion. Why 2D? Because this is very cheap and runs in less than 10 seconds. And for the sake of this tutorial, you will see that once we go and look at the 3D code, the code is exactly the same. The only difference is that you are passing a 3D array instead of the 2D array. So what we do here, we just take a middle inline, both for the data and for the acoustic impedance model. We make sure we bring the model into, apply the natural logarithm like the modeling equation requires. And then we are ready to go. So here you may wonder what this is. Well, when you do statistical wavelet estimation, you don't have an accurate estimate of the absolute amplitude of your wavelet. And so there are different ways. In this case, I'm back guessing the number, taking it from a well tie that I did somewhere else. But you could also just try different numbers and see how much of your seismic data gets added to the background and compare results, for example, with well locations and see where you are satisfied. So this is what we say in this case is a PyLops app. We generally like to provide very low-level features, operator solvers, but for a few interesting problems where we see that PyLops performs very well, we always try to create small self-contained routines where users can just provide data and additional information, and the operator will be made under the hood for them, and inversion will be performed under the hood for them. So for this post-stack inversion routine, it's fairly self-explanatory. You provide the data, the wavelet. If you have a background model, like in this case, we provide a background model. And everything else is details on how you want to solve the inversion. We can solve it explicitly by creating a dense matrix. That could be a very good idea for a first step where we invert trace by trace to get a refined background model. Or you could do it straight with a linear operator and simultaneously where we solve the entire model at once. That's what we're going to do here. And we can add the regularization both in terms of Tikhonov and L2 regularization with a gradient like I discussed above. We could also add L1 regularization for the second problem we're going to solve, and we will do that later. So let's run this. Okay, this is faster than I expected, already finished. And we can bring the model back to its real values by applying the exponential. Remember, we had to apply a logarithm. And now we visualize the results. So what we see, if you're familiar with seismic inversion, this will look very familiar to you. If not, let's go through one by one. So here is the seismic data. This is what we want to invert for. And here is the final residual. Ideally, we would like to mesh the data as much as possible, but by adding a regularization term, we ask our inversion to match the data misfit only to the point that is also satisfying a regularization term. And the more regularization, the less will be possible for us to match the data in full. But ideally, you don't want to match the data in full because data will be contaminated by noise. And you see in this case especially, we have tried not to match these very low frequencies because the background model already came as a starting guess to the solver. So here we see the background model, and now we see the inversion. So everything that was not in the background model is what the seismic provides you with. So background model, remember, is mostly information that you can get, for example, when you do velocity model building, or if you have many well logs, many wells were separated from each other, you could do any sort of geostatistical interpolation to get the background model. But this is generally, or you should generally have it smooth because you're not very sure what happens in between the wells. Anything that gets filled here is the information that seismic brings. And this is, at least for me, looks quite nice for the Volve data. I have seen other results, and I think this is among the most interesting one that I have seen. And this is what we get if we now subtract the two. This is what you could call a relative inversion. It's not absolute values. It's just the blue is increase and red is decrease. And what we see here is mostly really what the seismic is bringing to the inversion. And a few interesting things that will come back later. We notice that because of the acquisition on the right-hand side, we have a sort of dimming in the amplitudes that is clearly not geologically meaningful. It's more due to the quality of seismic data. We also notice that every time you go from red to blue, we have quite a smooth transition going from red to white and blue. And this is due to the fact that our solution, L2 solution, tries to be smooth by nature, and even more smooth in the x direction because we try to impose that. So what happens if we now want to add a bit more blockiness to the solution, so have better jumps, at least in the z direction? Well, it turns out that you can do that by adding an extra regularization term, as I said before, but solving that problem is far from being trivial. And up until, I think, early 2000, we had some solvers, but they were not very efficient. It was only in the early 2000 and 2010 that more advanced solvers started to appear in the mathematical community. And one of the most popular is the so-called split Bregman solver. So we have this solve. Yes?
A quick interrupt before you continue. Doug has a question in the chat. If you could do the inversion without passing an upfront background model?
Yes. Who's asking this?
Doug McClement.
Oh,
Clement?
yeah.
Don't
so let's
take
do it.
me up on English pronunciation.
Let's do it on the fly. So I'm just commenting out this. I think I know Doug, so I think is familiar with the concept of relative inversion. So I guess that's what he's asking. So I'm taking the model out, and now let's take away some stuff. And now let's try to look at this. So we are basically just starting from a 0 background model, and we cannot expect the seismic data to give us very low frequencies because the wavelet has unfortunately removed those frequencies. But yes, PyLops can also run, and what PyLops gives you, okay, very, very big, it's 10. What PyLops gives you is a relative, is a relative velocity, not velocity, sorry, acoustic impedance model, which I'm going to plot with the same color. And you can see it here. If I were to, give me just 1 second, if I were to center it to 0, 2.5, so maybe -2, -2. Clearly not what I want. Okay, so I'm failing miserably. I'll get back to you. It is possible. It's definitely possible. Now I'm not in. Oh, I see why. Because I should not apply the exponential. I should only apply the transpose, because now it's not anymore a physical quantity. So this is what we get. You see, we go from seismic data that are wiggles across interfaces to more layer looking like geology. Of course, the numbers are meaningless. It's just relative. It's maybe more interesting if you do 4D inversion, but hopefully this answers your question, Doug. And Dieter, let me know. If not, I can always go back.
Yep, will do. Thanks, Matteo.
Good. So yes, let's put it like this. If you don't have enough time, if you don't have a good knowledge of your background model, a relative inversion is good. But as you can see, it's just one change in the code. Of course, a lot of work possibly to get this good background model, but I always recommend, if possible, to do absolute inversion, because that gives you much more, and you could tie it to rock physics and tie it to, for example, phases. But of course, relative inversion sometimes is good enough for tasks that we do in the oil industry or any industry dealing with seismic data. So I'm going to the split Bregman because this is a quite exciting, I will say, solver. It's not the most straightforward solver. I was quite surprised. I could not find a good implementation in Python at the time. I decided that we will implement it ourselves. And even if we found a good implementation, unlikely, most of the implementations you find online, they are not allowing you to use SciPy linear operators. They're only allowing you to use NumPy matrices, unless they are in the SciPy sparse library. And so we just went ahead and made our own split Bregman. And if you run it here, you will see it takes a bit longer. If you look at the results, okay, now I think it's running code on the fly, probably destroyed something. Let me just quickly go back to, oh, actually, okay, let's try to rerun. We're gonna rerun the split Bregman, and now we get the right plot. We see the residual is slightly different. We see that more higher frequencies are now appearing in the residual, and the reason is because by trying to enforce jumps, we are kind of forcing the model to provide us with high frequencies that we don't really have in the data. And so when the two are crossing, the regularization term is actually dominating and making his own choice compared to what the data misfit term will ask us to do. But by doing that, we get a model that, at least in my opinion, is nicer. You see you have nicer, more sharp jumps between, especially at this very strong top reflector here, but pretty much everywhere. Nevertheless, you seem to have been boosting quite a lot also the low frequencies, which could be good. It's something you want to do generally in inversion. But again, here where we had the edge effects before, our inversion looks a bit funky. So is this the end of the story? Well, no, it's not the end of the story. It turns out that if you look into the literature of so-called convex optimization, there are even more interesting solvers that have emerged in the last 10 years. I would say before mathematicians, they all turn into machine learning in these days. And some of these solvers are really, really interesting. And some people have actually started using these solvers in combination with machine learning. So these solvers are referred to as proximal solvers because compared to standard gradient-based solvers, they add an extra step. So in gradient-based optimization, as I mentioned before, you estimate the gradient at each iteration and you go towards the opposite of the gradient if you try to minimize your cost function. In these solvers, you do this step, on top of which you apply what is called the proximal operator of your regularization term. And by doing that, you allow any regularization term to be included in your cost function, being it both smooth and convex, but as well as non-smooth and convex. For example, a TV regularization is non-smooth, a normal L1 is non-smooth, or if you add constraints like box constraints are non-smooth. So for this, we realized that there was a bit too much work to do, and probably it would have required a bit of restructuring of PyLops, and we were very much against that. Because we would have had to push to version 2 or do some breaking changes. So instead, we made a sister library called PyProximal that implements a variety of these proximal operators, one of them called Primal Duo. And the feeling is very similar because under the hood, when we do the linear operators, we are using PyLops linear operators, and we enrich it with what we call the proximal operators. So the setting up of the problem is very similar as what you do in PyLops. Here you create your modeling operator, and you say that you want to have a L2 term in your cost function, where this is the operator and this is the data. So this is basically your misfit term. You say you also want to have a regularization term, and now we're going to use a TV regularization that, if you are familiar with it, is a L2-1 norm of a matrix, and the matrix is computed by applying the gradient to your model. So you do the gradient, means derivative over x, y, and z. You shape them into a matrix with 3 columns, and then you do L2-1 norm. Now you want to combine these two, and this is what you do with any solver in the PyProximal library. So compared to PyLops, where you had an operator and the data, now here you have 3 elements. The first one is your smooth term, in this case the misfit function. The second one is your possibly non-smooth term, which in this case is the TV norm, or could be a box constraint or any other indicator that is non-smooth. And then again, you provide your operator that goes in combination with this non-smooth term, and the initial guess and few other parameters. I'm not going through the details. If you are interested, let me just pull it up. We have a exact same setup that the one of PyLops. We have a documentation here. Okay, at the moment, read the docs is sleeping. See if it's me or them. Yeah. Let me see if I can get it. No? We'll get back to it. It's the exact same looking like documentation that you will be able to look into it if you're interested in this type of solvers. But let's first run it. You see it takes a bit longer because eventually solving a nested loop of least square optimizations followed by some of these proximal projections. We're going to run it a bit longer for 50 iterations. For 2D is still very fast, 19 seconds. And we will see the results. Again, to the eyes, these results don't look very different, but if you look a bit more into the details, you'll see that you have recovered some of these sharp discontinuities much more than the L2 solution. They're more similar to what you had in the split Bregman, but the solution actually seems to be a bit more stable. You get these nice thin layers, as well as a fairly nice boost of the low frequency here without the funny looking artifacts that you got in the split Bregman solution. But again, these are different results. I'm sure the subsurface is neither of these three, so it's more for users to try different options, and depending also on the time they afford to wait and the data. Sometimes I've seen some data where split Bregman didn't really give a benefit compared to least squares, and some data like here, the Volve, where it looks quite nice. It also boils down to how good is your estimate of the wavelet. So with this, we still have maybe 15 minutes or so. So the one thing I'm going to do without running the code is to just show you how you can run 3D inversion, so the full 3D cube in the area that we have selected. You will see that the code is pretty much identical. Again, we can call our post-stack inversion one-liner routine, and now we pass the full data. And we could do it also with the sparse split Bregman solver. When I run this on my workstation with 8 CPUs, quite a good, powerful workstation. And we got this in about 32 seconds. So not terrible for a 3D dataset. And if you look at the results, they look almost identical to the 2D for the same inline slice. But we can also now look at something that I find always fascinating when I look at seismic data, a single time slice. And you see this is what the data looks like, this is what the background model looks like, and this is what we get from the inversion. Many more details and possibly room for better interpretation of how the geology in this area look like. We have also run the Primo dual solver. Now, this, as I said, is a fairly expensive solver. It takes quite some time. And although it takes, of course, longer, once again, I tend to like the results a bit more. In this case, especially if we look again at the time slice. But as I said, this is not always a gigantic improvement, and it's more to you to decide whether you are happy with smoother models or you want sharper models. I would say if the model is just for some manual or visual interpretation, probably least square is good enough. But if you want to use those to condition, for example, geomodels, I would say that the less smoothing between formations you can afford, they're probably the best you can get. Now it comes to the very last 2 cells of my notebook, which, as I said before, I'm not going to be able to run them here because I do not have a GPU. But it shows the powerfulness of the new GPU backend that we recently introduced in PyLops. So what is the main difference from the user side is that when you feed an operator or a solver, or in this case, the post-stack inversion routine, you want to feed them with the CuPy arrays instead of NumPy arrays. So here, if you're familiar with CuPy, by invoking CP as array, you will take the NumPy array D and ship it to your GPU. And the same you do for your background model. And then we do it the same here on the fly for the wavelet. Now, if we run this least square solver, I'm just going to go up here just to remind you how long it took. It took about 32 seconds of my 8 CPUs machine. If we now run it on our GPU, I'm using, in this case, a RTX 3090, and this is what we get. 1.7 seconds for the solver itself and 1.8 for the exact same amount of operations, just to be fair. So you see that once you have access to a GPU, if you have access to a GPU, you can really leverage even more the power of matrix-free linear algebra. The fact that you can use a GPU is because we are really being as conservative as possible with memory requirements. Nowadays, computers have fairly big memory. They can probably forgive you in some case, but GPUs still have very limited memory. So you will not probably be able to run this with a dense matrix on a GPU. But you can do that with the matrix-free linear algebra, and you can get fairly big speed up, even though you will, or your friends will tell you that this code is all Python code. Eventually, under the hood, most of the operations will be CuPy, and so will be running on a GPU. And if you're careful the way you do it, like in our case, your data will never leave the GPU from this time all the way to this time, where you are just bringing this back to the CPU to be able to visualize or save to a file. So I think, Dieter, for me, I think we are done. I just leave some time for questions if there are, or if you have any yourself.
Yes, I would certainly have some. Let me see if in the channel are some
other.
Or while I think about it, I ask if you think. So in the beginning, well, early on, you had this PyLops GPU, right?
Yes.
So is that now completely integrated into PyLops, or?
Good question. So PyLops GPU, I would call it a half failed attempt. At the time, I thought that PyTorch was a good route to implement some of the operators. It turned out that, yes, was a good route. We were getting good performance, but it was a massive effort to re-implement them. And CuPy was just, I would say, a bit immature, in my opinion, 2 years ago. But when I revisited this a year ago, then CuPy was clearly at a different level of maturity. So what we did was take all the implementation that we have in PyLops, do some tricks in the backend, and make sure that if you provide CuPy arrays, will trigger CuPy routines, otherwise will trigger NumPy routines. And that also helps with the fact that NumPy in the last year or so has been very good at releasing array functionalities, where under the hood, in most cases, they actually realize this for you. So if you pass a CuPy array to a NumPy function, we'll do that. It is not so straightforward, because when you do things like instantiating an array of zeros or an array of whatever, if you say NP will instantiate a NumPy, so if you want to use a CuPy array, you need to kind of understand that. That's pretty much what goes under the hood, but most of the time we really leverage this interoperability. So PyLops GPU never progressed in creating more operators, but it's still there, and I think will stay there, because as a very nice functionality, which is, let me actually pull it up, which is called, I would say, it turned out to be a library where the only thing that I would suggest using is what we call the torch operator. Torch operator basically encapsulates any official PyLops operator and allows to chain them with any torch autograd function and get automatic differentiation for you by knowing that any linear operator, its backward is adjoint. So we only need to basically inform PyTorch of this. And we can also do it using CuPy and never leaving the GPU. So the data will flow between torch and CuPy operations, but will never leave the GPU.
But you don't plan, if it's just this function, you don't plan to bring it into PyLops main?
I have been thinking about maybe someone from the community or you could provide a feedback or suggestion. The only reason I didn't decide yet to do it is because, well, it could be brought as an optional. I don't want to have PyTorch as a hard requirement.
Yeah, but that would be, we could think about that. That would be easy to implement as a,
So only if PyTorch is installed, then you can use it. And we
and
do
what
similar things.
And similar question for the PyLops distributed, I guess, with Dask, or what did you use there?
Yeah, so PyLops distributed is for Dask, is a bit more mature than PyLops GPU, is actually being used for quite some advanced research in the area of redatuming. We have a paper coming out soon. And again, whether we should bring it into the main PyLops or not, I'm not that sure, but I think we got quite some good speed up, or not. It's not always about speed, it's about when you really need big memory that cannot fit in a computer. This is where PyLops distributed and basically Dask, I think, has very good potential. So yes, these are sort of sister libraries, and the same for PyProxima, which I'm just showing now. I think eventually maybe we'll make it into PyLops. It's just because when you start something, you don't want to do something half-baked and then realize it's in your main library. So that's why so far they are still out.
So I don't know if you have the chat open, Merwan Hamdani.
Yeah.
Ask how you will see the future of the inversion problems in PyLops. What are the remaining aspects to dig into? I don't know if he means that from a contributor perspective, where he could help, or more general. Probably both.
That's a good question. So I will say two things. So one, in terms of applications, when we started PyLops, we tried to make some notebooks and some of the tutorials in the documentation that are not only geophysics, but they were kind of toy examples. If I just go here in the documentation of PyLops, you have some sort of image deblurring, some simple CT scan imaging. They are fairly, I would call them naive examples, just to show the functionality of the library. But in the last year or so, since we published our paper, it's actually become very easy to follow up if anyone uses PyLops. And we have seen publications in astrophysics, in medical imaging, and just today I noticed this publication using microwaves. And so one thing is really the application, where this library could be used to do some nice research in which domain, and what is missing. Because, for example, for the astrophysics work that was done by University of Durham, they use the so-called NUFFT, which is a FFT over non-uniform spacing. And that one we had not implemented in PyLops, and they actually implemented it themselves as a PyLops operator. And we had been chatting whether we should bring that in the main library. So this is where I see more the future, more onto needs. If someone wants to solve a problem and sees that something is missing, that's where we should put more effort. I see that with CuPy evolving as well, multi-GPU could be around the corner, hopefully. I think CuPy is working a lot into integrating multi-GPUs in an easy way. And for the Dask, I'm very keen on continuing along that direction, and I have people as well that work with me that are very keen. It's a bit harder for anyone using Dask. It's not always straightforward to tell how to make Dask work well. So if anyone is very good with Dask and has interest in inverse problems, I'll be very keen to hear from them and get some help and contributions, both in reshaping the library, maybe something is not as good as it could be, as well as evolving it further.
And then, yeah, it's cool because the tutorial today had first a general introduction to linear operator, and then with the horizons and the post-stack inversion, a focus on geo as we're here in subsurface. But PyLops is a very general library, and I remember in the beginning we had these discussions if you want to split it up or not. Where are you? Where are you in this process? Will you split it up, or you will keep it like this? Or
It's a good question. I think we always postponed, and I would say by now perhaps we could split it. The only worry I have by splitting it is that some people that are more interested, let's put it like this, to do science than dealing with the Python environments and missing library and so on and so forth, all of a sudden some of their codes will not work and they may get confused. So that's my main worry. When you make a library into a 2.0, it needs to have a reason for that, right? I think TensorFlow had a reason. They realized that their pattern wasn't the best, and then they made it 2.0. And other libraries, of course, have other reasons. But just to say, PyLops is a fairly small library and is on a 1 point, and you have a library like NumPy and SciPy that are on 1 point. So really saying we want to go to 2.0 is a big statement in a way. If those libraries can stick to 1, then I think we need to have a very good reason to do that. And I'm not yet convinced. But of course, anyone else that contributes to PyLops should bring their reasoning to the table there. And I'm happy to be convinced. And
you could also split the geo stuff out, but have it as a requirement for PyLops and raise a warning for a year or two.
Yes,
that in the future it will be an own library. Yeah.
And say that at this point it is still all working, but be careful.
Exactly.
Yeah, I agree. I mean, it's also about timing, making sure you have time to do this. At the moment, it was not my priority because things work, and if you have 10 instead of 5 operators, shouldn't be a huge deal if you only want to use the 5. But I agree, in the long run, will be nicer that only the core stuff are into PyLops, and then a few more geophysics related are into another one.
Cool. I'm quickly asking in the chat if there is anything else. And otherwise we can wrap it up. Doug is writing. Let's see.
Sure.
Let's see how fast you can write.
We have 8 minutes, so no rush.
Yes. It's not very strict on times. We can stop early, we can stop late.
And I always say there is an elephant in the room that I don't know if I have interest or time, but you, Dieter, for example, could be a right guy to implement also non-linear inversion, right? Mm-hmm. That could also be an interesting... I mean, proximal operators are, in a way, non-linear, right? But I'm talking more about things like full waveform inversion and a joint state type of problems.
Yeah. Kieran says, thank you, that was excellent.
Thank you, Kieran. Hopefully you got more from the postdoc after you asked the question last week. Just let us know if you still missing something or need some help.
Let me see, what is, if I look at the library, what is the curve lops?
Okay, yeah. Let me just do this very quickly here. So
yeah, go through what
now
you
we have since I left Equinor, we decided together with my colleagues in Equinor would be easier to just push PyLops to his own organization, and it's still open source and everyone can use it. And if you look here, we have quite a few of the tutorials that we have been giving, as well as the main libraries. And one of them is CurveLops. So CurveLops is fully work of Carlos. You didn't know him. Maybe some people in Zwang know him. He's a former colleague of us in Edinburgh. He did his PhD as well. And this is a wrapper to the famous curvelets from the Curve Lab C++ library. So we just wrap it with PyBind and made PyLops operators on top. And curvelets are fairly popular in different domains, seismic for sure. People like me that work with interpolation problems, we really like curvelets. But yeah, unfortunately, it's not that straightforward to get the code to be installed. We succeeded in various places. Unix machines, more likely Mac with a bit more push and pull. But actually, Carlos just last week made a Docker container for CurveLops. So if you are familiar with Docker and you don't want to cry installing FFTW and CurveLab libraries, you could try to use this Docker image.
Cool. Cool. So there is Doug says, sorry for the focus on band-limited inversions, but I work a lot with colored inversion. How would I approach this in PyLops? Only done in commercial software, he says in brackets.
Yeah, so if I understand you correctly, because the jargon sometimes is slightly different, okay, the code I just removed, the one where we took away the background model, that one is what I call colored inversion. It's not, I had this discussion before, I can't remember with who, it's not what, if you look at a famous paper, colored inversion that does basically spectral balancing, this is not the same. But in my opinion, this is a more formally correct way to approach this problem from a mathematical point of view. You frame it as an inverse problem and you solve it without a background, which means you can't recover the low and the high frequencies because they are not in your data, unless you add some regularization like TV that will push your frequency a bit more. But what you get is really the exact same as colored inversion, is variations with respect to an unknown background. And I used it a lot myself in Equinor, this code and the colored inversion, because the results are nice. And sometimes, as you say, colored inversion is good enough and you don't have a good background. Hopefully,
he says he means convolution with a minus 90-degree phase operator with spectral shaping.
Oh, I see. Okay, that's what I actually meant. That's the paper. Let's put it like this. It's the last minute. I don't particularly believe that's the best way of doing colored inversion. I believe that framing the problem as an inverse problem is a better way. That's what you can do in PyLops. But I know that in the industry, people are stuck to routines because they work well and they have performed satisfactorily. So in that case, PyLops cannot do that for you because it's just a signal processing problem that it will be shooting a pigeon with a air gun, with a huge gun. Instead, just do it simply using SciPy and go into the frequency domain. But if you want to try to solve it as an inverse problem, that's, in my opinion, the way the problem should be framed. And you can choose either of these three, provided you don't pass the background. Then what you're doing is a colored inversion, in my jargon at least. That we can talk offline, because I had similar questions in the past from other geophysicists that are maybe not so much into inverse problems, but we can discuss why these two things are fairly equivalent from a mathematical point of view, at least.
I think we can continue that in the channel, and then I'm gonna wrap it up here.
Yep.
What do you think?
I think I'm gonna be on my computer, so anything on Slack, whether it's on this channel or on the PyLops channel, will do, and I can answer. Or reach out to me directly. That's also a good enough way.
Great. So thank you, Matteo, for this tutorial.
Thanks a lot, Dieter.
That was really great.
All the organizers of Transform for this opportunity.
Yeah, I finish off with thanking our sponsors again, StudyX, AWS, Agile. And if you liked what Matteo presented and if you like what Transform 2021 brings to you, do what YouTubers do and subscribe, like, share, and spread the good word. Have a good day. Bye-bye, everyone.
Bye, guys.